And welcome back, everybody. So today we are switching gears a little bit, and we're going to start our section on Darcy's law, but from first principles. So this very lecture will be on reviewing basic physics concepts, and then we will circle over the next three lectures back to deriving Darcy's law, basically from these very fundamental laws of hydraulics. So the first place I want to start, so in this section or in this part of the course, we kind of flip the script, right? So far we've derived Darcy's law from empirical perspective, so from basically, using his permeameter and doing experiments, lab experiments, and demonstrating sort of how flow through porous media works. Now here we'll start with the physics. So there's a couple things, and I put the pictures of Einstein up there and then Newton down there. So you can try and remember either one of those two things. So depending on how fresh your physics courses are, ideally what we start with is Newton, right? Always in physics. So we start with a force, which is an accelerated mass, and that's Newton's second law. If somehow you don't remember that, remembering Einstein is always a good way to go. So Einstein said that energy is mass times the speed of light squared, right? mc squared. So if you remember one of those two things and a couple more definitions of physics quantities, then chances are you can kind of go through the following slides and derivation. So what you want to remember is dimensions, basically. So if you think of in terms of dimensions, so mass, length, time, here MLT. So the usual system is mass, length, time. That's your three basic dimensions. So you want to remember those. I put a couple of examples of BLT sandwiches because as I was preparing the lecture, somehow I kept thinking of BLT for MLT. And if you make a BLT vegan you think of the meat as the mass, then you get MLT. Force here and energy, right? So definition of a force in the FLT system is a force. And of course in the MLT system, since it's a mass accelerated, so acceleration is length per time squared, right? So it's velocity per time, right? Is the change of velocity over time. So it's a velocity per time. So it's a length per time, the velocity, divided by a time, the acceleration. A force. Now the energy, you will remember probably that it's force times some distance, right? It's the definition of work. You have work down here as well, which is the same thing, of course, right? It's a force times a distance. And that's kind of the definition of work in physics, or energy, right? And then, of course, if you convert that in terms of the MLT system, right? Well, then it's just MLT minus 2, right? So the mass times length per time squared for the force times another length, right, for the energy, right? So you can get from dimension to dimension very easily. Okay, so again, those are noted down here. Okay, so let's start here, right? So Newton's second law is stated in his natural philosophy and mathematical principles of natural philosophy, published in 1656, I want to say. 1686, that's right, 1686. So this is an illustration, of course. Newton, you'll remember the story of the apple that falls and, the weight of an apple, the difference between mass and weight, discovery of gravity. So many achievements and accomplishments, of course, but the law we're interested in, right, states that the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. In layman's term, or in today's terms, that means if we push on something, it'll go faster in the direction we pushed it, and if it's not too heavy, okay? So in other words, the acceleration equals net force over mass, right? So if it's really heavy, it won't go accelerate much. And of course, if there's no force on it, it won't accelerate. And the more force, the more acceleration. And because those are vectors, then, you know, if you push it one way, it's going to accelerate that way, okay? Oops, excuse me. All right, now, going back to fluids, so that was our basic introduction or reintroduction to physics principles. Now, if we bring it back to fluids, right, what does it mean for hydraulics, basically, or for fluids? So if we're talking about the accelerated mass, you can see here for fluids, we can write this as rho du dt. So again, u here in those next few slides is going to be velocity, right? So change of velocity over time, again, is acceleration. Now the mass for a fluid, we think of density, right? So it's really a mass per volume. So all those terms are going to be per volume, right? Per unit volume, if you will. But it's the same thing, right? We have a mass, we have an acceleration, and again, we now normalize per volume, per unit volume of fluid. And then the forces acting on the fluid are, you know, the gravity, of course. So if there's, you know, open channel flow, for example, flows down gravity, and groundwater for this course also flows down the head gradients, right? So gravity is going to push water down, right? Now pressure forces, for confined aquifers, right, we do have potentials and we do have pressure forces. And then of course viscous forces, so, you know, the more viscosity, the more resistance to flow there is. So there's some friction around the grains, especially in groundwater. There's a lot of friction because we're flowing through a porous media. So each pore, each grain of the matrix, right, exerts friction on the fluid. So if we write out if we write out these different forces, we get to the Navier-Stokes equation. And I put here some representations of those two gentlemen. So Navier, already talked about him. He's a French guy, you know, and he was at the École Polytechnique at the same time that Darcy was there. So he was a mentor for him. Stokes is a little later. You can see from the dates, right? He was born when Navier died, Stokes was studying. So he actually contributed to some solutions of the Navier-Stokes equation. We still talk about Navier-Stokes equation, but really Navier came up with the equations and Stokes with some solutions for specific cases. Stokes was a professor at Cambridge. Okay, so if we write out these different forces, right, gravity, pressure, and the viscous forces, we get the Navier-Stokes equation. So Stokes was a professor at Cambridge. You can see that his dates don't really overlap with Navier that much. So Navier really came up with the differential equations that we know as the Navier-Stokes equation, but Stokes really provided some solutions to the Navier-Stokes equation, but in very specific cases, and we'll see some of that in the following lecture. But for now, right, we can write that the acceleration and mass, or rho du dt, equals, so again, the gravity, so that's rho g, so rho, again, the density times the gravity times the difference in elevation, right? So that's a potential energy due to gravity if you want. The pressure forces, so if there's pressurized flow, there's pressure forces in the fluid that need to be accounted for. And then finally the viscous forces, so mu here is viscosity, and then del square u here is the second derivative in space, spatial derivative of velocity, right? So again, what's important here is that we have gravity, pressure, and viscosity going on. Now, reminding us of the definition of a head, right, that we did a lecture on before. So writing the head as, you know, the pressure head plus elevation head, we can replace now those two terms into a head term, which is here, and write that the accelerated mass equals, you know, the change in head, basically, and some viscous component. Okay, so this is the Navier-Stokes equation. This is a simple version, if you will, of the Navier-Stokes equation that we'll then use to derive the Stokes equation and the Poiseuille flow in the next lecture. Okay, so far we've reviewed some basic concepts of physics, wrote out the different forces that act on a fluid, so the basic Navier-Stokes equation, and I thank you and we'll see you in the next lecture.